My name is Matteo Salvarezza. I am the lead developer of the neural network framework at Wolfram Research. And this talk is going to be about future design extensions to the neural network framework. Specifically, future design extensions that will be unlocked by the switching that we are in the middle of. We are switching our backend for computations from MXNet to PyTorch. First, I'm gonna state what the current status of the framework is and the current design of the framework in regards to the critical points that I'm gonna address, and then I will discuss the future extensions of those points. So, okay, first important concept is the concept of the static framework. So the current design of the neural network framework is that of a static framework, which ultimately stems from the fact that the backend used for computations, in this case MXNet, is also static, or at least the part of MXNet that we are using is static. So what does it mean, static? Well, static means essentially that before a computation can run, you have to know a lot of things about what will happen in that computation. Specifically, you need to know all the operators that are going to run and what is their input and output dimensions. So these properties reflected back on the top-level framework design. So and so layers and containers need to have a static input shape set so they can run. So for example, this is a layer that's ready to run, and I'm setting the input shape. It goes to 3 here, so this is a vector of length 3, and the static shape inference in the framework is setting the output to a vector of size 2. Now this is a layer that everything is specified and can run in the backend. Same thing for a container. I can define a net chain. I can set its input shape. Shape inference will fill out the intermediate and the output shapes, and now this is a network that's ready to run. For this, we know exactly what operators are going to run, in this case, these two, linear layer and the ramp, and we know their input and output shapes. This is a static framework. Now, there are two aspects of the framework which can make you think that what I just said is false, but it's just an illusion. So first of all, you can actually evaluate layers with unspecified input shape. So in this case, I haven't set anything here. This input is a generic array. I'm just giving a number to it, and this is just running. But the way this works because we are silently doing this operation under the hood, because we know what the shape of the data the user fed. In this case, it's a scalar, so we are setting this to a scalar. Now we have our network that has an input shape set. So, and then we can run it. So this might seem unimportant, but in fact it is, because doing this operation takes time, and you can compare the execution time of a layer where the input shape is specified versus a layer where it's not specified. And you can see that it's more than 10 times lower to run the unspecified layer. So yeah. Another aspect related to this is that you can set the first dimension of some input shapes and output shapes to a string that says varying, which means the length of that dimension can change. Okay. So again, this gives the illusion of a non-static framework. In this case, I have this layer that takes an input shape of varying, 3, and I can feed it sequences of length 1, length 2, length 3, or whatever, and this is going to work. Well, now, first of all, this is only for one dimension, so it's not general, and also this still works because there is, under the hood, we do an orchestration of several static MXNet graphs, each of which operates on a fixed sequence length. So there is actually multiple MXNet graphs that are associated to this network. They all share memory with each other, and we run whichever we want depending on the sequence length. And if you feed a new sequence length, and there is no pre-existing static graph that operates on length 4, we create it and cache it. So, and thanks to this caching, performance in this case is similar to fixed length. So I have the layer with varying 3, I have the layer with 3,3, and I can evaluate them both on a sequence of length 3. And you can see that the performance here is not, it's not terribly worse. It's, yeah, it's a factor 1 point something, while here it was a factor of 10. Okay, so yeah, take away things from this slide, like the property of a static framework. Now, let's now talk still about the current state of the framework. Let's talk about integration with the rest of the language. So we have 2 entry points for that. One is function layer, one is compiled layer. So function layer, it takes a function that mixes ordinary Wolfram language code, such as like ramp, tanh function, cosine, exponential, whatever, and neural network layers, so linear layer, aggregation layer here, and turns it into a neural network layer that you can use freely as a generic layer. So this is the function layer from this function, and now this is a layer, and I can put it into a container. Here's a function layer. I can do anything I can do with normal layers, I can do with this. Now, the way this works is it scans the function body, and essentially, well, when it finds a layer, that's easy because we already know in the neural network framework about these things. When it finds expressions that are not neural network layers, it basically translates them to equivalent neural network layers. So it scans the function body and creates an equivalent net graph out of it. And you can see it by, if you click on this plus sign in the function layer, there is a parameter which is called net. And you can click on this, and it's going to show you the net graph that it has created from this code. So this is a graph that performs an equivalent computation purely in terms of neural network layers. Okay, so for example, like obviously, like this is a very simplified example. It can do things that are more sophisticated than this, but here it's just, you know, there are some mathematical functions that is just expanding into the element-wise layer of the associated to that function. So we have this ramp and this tanh, etc. Even more directly, you can just wrap function layer into net graph, and it's just going to give you the net graph. There is no function layer anymore. It's just net graph. So function layer is just a translator. Function layer is something that translates Wolfram language code to neural network layers, essentially. It does a little bit more than that because there is a few primitives which don't translate to other layers. They just stay function layer. For example, if you feed the determinant or the dimensions, or if you use these functions inside a larger body, it will create nodes that are just function layer. And you can see that here, net says none. There is no net associated to this. But this still runs in the backend. So function layer translates Wolfram language code to neural network layers. Neural network layers are translated to the backend, whether it is MXNet or PyTorch or whatever. So in the end, function layer is still going everything through the backend. Compiled layer, on the other hand, doesn't. Compiled layer takes a function object that you can pass to function compile, so which has compiler type annotations like these, and essentially uses function compile to produce a low-level compile code that we can plug directly into the backend. In this case, MXNet, because this is the only backend where this works is MXNet for the moment. So this is creating brand new low-level code that the backend executes as an external blob. Okay, so this is not translating to primitives of the backend. This is creating a new primitive, essentially. And yeah, compilation still takes some time. It's getting better with each release, but still needs some patience. Anyway, yeah, well, you already have the result here. Like obviously, it's gonna spit out a layer, and you know you can put this layer into anything. I should mention we can still compute gradients and backpropagate through this layer, and this is possible because the compiler has built-in auto-differentiation capabilities. So we're using those too, and you can compute the gradients using the compiled layer. Okay, now let's go to the extensions. Okay, now so what I will talk about here is things that will be possible after we finalize the switch to PyTorch, which is a dynamic backend. And yeah, they mostly stem from the fact that PyTorch is dynamic instead of static. So in a dynamic backend, you don't need to know basically anything about what computation is going to happen, because there is no step in which you compile a computational graph. You just have operators, you just run them as if they were functions. So so to start with, layers don't need a static input shape before they can run efficiently. So one could be able to run layers like this with no performance cost. Similar features are runtime reshaping and transposing, which is still about not having to know what the shape of things is before computation run. Okay, so at the moment in the framework, we can do reshape in these two ways essentially, and we can do transpose in this way. And in all these cases, you need to provide the specification of how you are reshaping, how you are transposing when the layer is constructed. Okay, so for reshape layer in this case, we have to provide the output shape explicitly here, or you can with this syntax you can create a port that basically means copy the shape out of this port, but you're still providing the shape just through a port. And with transpose, you are providing the transpose specification statically inside the layer again. So in all these cases, the output shape is known when the layer is built. There is no other way. But in a dynamic scenario, one can imagine, like, and I will use placeholder layer to represent these things. Like placeholder layer is a layer that doesn't do anything. It can't run. Like if you try to run it on input, it fails because it can't, and it's just there so that it can be a placeholder inside the network for something else. So one can imagine a runtime reshape, or it's probably still going to be just reshape layer, and we're going to like put this new feature inside it. But for now, let's imagine it's a different layer. So you can have a shape port that directly takes the shape as an input, and note that this case might seem equivalent to this, but it's not, because here we are feeding a tensor inside the layer, and we are asking the layer copy the shape of this tensor. Here we are not feeding the tensor; we are directly feeding the shape. Okay, and in particular, the shape in this example is a bearing. Basically it's a list of varying length. So the shape is always a list. Shape of stuff is always a list, and here you are just plugging the shape as a vector in the layer, and it's going to reshape the input to that shape, which is different from copy the shape of whatever this is. For transpose, same thing. We can expose a port that takes a varying, so a list of varying length of integers, and it's going to just be used as this. But here you got to know, when you build the layer, here you have you don't. Here you can run the layer and pass the transpose specification at runtime. Okay. So okay, still on the dynamic paradigm, dynamic branching in loops. So again, it's not just that you don't need to know what the shape of things is before you run. You don't even need to know what operators will run. Okay, so what you'll be able to do is to branch layer execution depending on the data, like this. You can imagine you can build a function layer, and you can process your data, and then you can put a check, and depending on, in this case, the total of all the elements of what I'm processing, I can either run this layer, that layer. This is just impossible in a static scenario. And a similar thing is loop with a number of iterations that also depend on the data. So I can have a loop that runs for n iteration, and n is decided at runtime. N is computed together with the rest of the computation. Or you can mix these two cases. You can have a do loop where you have an if statement inside and a break, which is, equivalent. Now, okay. So on the topic of language integration, one can imagine basically a mixture of function layer and compiled layer, where you have something that on the outside feels similar to function layer, but works in a very different way. Instead of scanning the body of the function and trying to translate every little statement to the neural network layers that are eventually translated to backend operators, you can imagine you have something which, if it finds a neural network layer, it just runs it eagerly without having to precompile anything, again, because the backend for the framework is dynamic. And if it finds something else, which is not a neural network layer, it can compile it on the fly and still run it eagerly. So this would be the best of both worlds for function layer and compiled layer, when you're not limited to having to translate everything, but by just compile whatever you don't know and run eagerly everything. Okay, last part is another topic, higher order gradients, which is also a new thing that is possible with PyTorch, and we cannot do with MXNet. So PyTorch supports arbitrarily higher order gradients, which you can request them during net evaluation using network gradients with higher order, or, and this is way more interesting, you can compute them inside the net as part of the forward pass. So, well, you will be able to. This is still a possible future extension. This is like, you can call this future extension essentially, not just possible. We are very sure this will look like this, quite sure, let's say. Okay, so at the moment, the neural network framework currently only supports first order gradients, and you can either ask the framework to compute the gradients during net evaluation like this, or obviously gradients are used during training. Now, on this scenario, if you want to expand to higher orders, there's not much to say. You can just imagine that you can do network gradient, your specification of what you want the gradient of, and just the order here. And this is going to give you the second order gradient, okay? But, so more importantly, computing the gradient inside the network. This could be done with a layer, okay? So I'm still going to use placeholder layer. So, okay, gradient layer, we imagine it takes one parameter, the order of the gradient, or this can also be another input actually. But let's imagine it's a parameter here. And it's going to take two inputs, numerator and denominator. And numerator and denominator is like, they refer to numerator and denominator of the differentiation operator. So like df divided by dx. So you are, in this case, you are taking the gradient of the numerator with respect to the denominator. So in your notebook, there was a slight mistake. This is not exactly the same thing, like the things were attached in this graph in the wrong order. It doesn't really change anything because nothing of this can run because it's placeholder layer, but yeah, this is the more correct version. So yeah, let's imagine you can use this layer and put it into a net graph like this. So what is this gonna compute? Well, this is being attached to the numerator port, this is gonna be attached to the denominator port. So in this case, this layer is gonna compute the gradient of whatever is produced by this element-wise layer with respect to the input. And since the output of this clearly depends on the input. This is going to give you some non-trivial thing in the output, and it's going to do it during the forward pass. This is not like it's actually back propagated in the backward, but from the point of view of the framework, it looks like just a forward pass of the top level framework. And it's going to give you in particular the third order gradients. Now, if you back propagate through this again with network gradient input, for example, then you would get the fourth order gradient. Or if you want to use a syntax like this, when you can put n here to get higher order gradient, then you're going to compute basically gradient of order 3 plus n, because 3 the forward pass gives you 3 already, and then you can request higher orders using network gradient. So okay, this gradient layer is going to unlock a nice application, which is the last thing I'm going to discuss, which is physics-informed neural networks, or more generally, training networks to solve differential equations. So, as an example, like let's consider a damped harmonic oscillator. So this is the equations of motion. We have the differential equation and the initial condition. And the goal here is that we want to model x of t as a neural network. So in this case, it's one-dimensional damped harmonic oscillator. The function x of t, it takes a real number, the time, and produces a real number, the position. So you can imagine you want to model it with this neural network, which takes a real and outputs a real. Now, we want to train this network so that the function implemented by the network becomes the solution to this equation, okay? And the way we do it is we enforce it in the loss function. So we define a loss function that looks like this. It has 2 terms, and essentially this term penalizes the training if the equation of motion is not satisfied, and this term penalizes the training if the initial condition is not satisfied. This alpha is just a relative scaling between these 2 losses that you need to tune the final loss function correctly. Okay, so let's try to implement this loss layer now, this loss function. Now I'm gonna set some the constants to this problem, so the mass, the dampening factor, and the elastic constant and stuff. And I'm gonna use this helper to create a gradient layer. And yeah, that's it. This is how you implement the loss in the framework. Let me copy this and put it here. Okay, so this big part is this term. And this part is the initial condition term. This is not interesting at all. Like, this is just x of 0 is a constant, is set to a number. This is just penalizing for going outside of that number. So this is just, it's just taking the initial position that needs to be computed by the network. So this is an input port of the loss, and just does that minus the initial condition squared. That's it. This part. So here we take as input, we take position. Position is x of t. So it's still computed by the network, and time is t. So initially, we connect them both to one of the gradient layers, which is going to compute the derivative of the position with respect to time, and so it's going to produce the velocity. This is first order gradient layer now. Then I can plug the velocity into another gradient layer that still uses time as denominator, and this will give me the acceleration. At this point, I get position, velocity, acceleration. I get all these 3 things, and I can combine them here using these constants and square them, and this is my ODE loss. So this is how you would do it. Now, to train this, the only other non-trivial thing to do is we need to provide both position, so x of t to the network, but also x of 0, okay? So what we need is 2 copies of the network that share the arrays with each other. And this is the final training architecture. So these are the 2 copies. These share the arrays. This takes the time as input. So this computes x of t. And this is attached to a net array layer that just contains the array 0. So this is T0, okay? And this produces X of 0. So now we have X of T, X of 0, we have the time, we have the loss, we put everything together, and this is our training architecture. And we can just, we will be able to put this into an array. At this point, training data is just a bunch of time values. There's nothing special in training data anymore. You know, all the knowledge is not inside the data in this case. Knowledge is purely inside the loss function. It's the physics. So you've got the times, which is your training data. And for combining the losses, you could either like add a threading layer here that takes these two terms and sums them with the weight you want, or you can do this. You can use this syntax in the train, which specifies the two output names of these, and the alpha scaling for the initial condition loss. And that's it. Now, obviously, this doesn't work because this tells you, hey, you have a placeholder layer, you cannot do anything with it. But yeah, this is what it should look like once we actually add the layer. Okay, so that's it. I can just mention some important performance improvements, and you can check my talk on the last day of the conference for more coverage about this. But with the PyTorch backend, we're getting native GPU support on macOS, which is a very big one because since NVIDIA divorced from Apple, we didn't have anything on Mac for GPU, and also no precision types and quantized types. So that's it. Oh, I realized there were questions. Okay. I was expecting to. Okay. Anyway, so, sorry if I didn't notice those. The specified layer is quicker than the specified layer, correct? No, yes, the specified layer is quicker because it's already it's good, it's ready to go. The unspecified layer needs to become specified first and then run, and so it takes more time. Is there a way to pre-train an architecture from websites like Hugging Face to also to import pre-train an architecture from websites like Hugging Face? Short answer is no. We just discussed it in the ML office hour, which was just before my talk. The problem with doing that is that at least for PyTorch models, but most of Hugging Face is PyTorch. PyTorch doesn't really have a model file format that you can just import into something else and represent it. They have files for the weights of the model, but the architecture of the model, which is, this layer should run first, and then you should, pass the output to this other layer, and so on and so forth. That stuff is not represented in a file. That stuff is just the code. That stuff is just Python code. So it's very hard to package that. Like, short version of the answer is it's very hard to package that. It's not completely hopeless, and we should get to it at some point. But yeah, at the moment you can't. But you can. I mean, the best option is the neural net repository because like the most important models that coming out from there, we are converting. So you can find some of those in the neural network repository. Okay. Could you share your NB file? I believe it was like you can go in the page of the talk, and there should be a link to download it already. Yeah. Okay, I see. We are out of time. So if there is no more questions, I will end the stream.